Alright guys, welcome back, and today we're looking at finding the determinant of a 2 by 2 matrix. Now, as far as determinant goes at this level, we'll only be looking at finding the determinant of a 2 by 2 matrix. So that's important to note. So as far as we're doing this, we're only dealing with matrices that are of the order 2 by 2. Now, before we look at an example, first thing I want to point out, if you have a matrix called A, right, then its determinant is denoted like this. So you have a letter A with 2 strokes there. Similarly, if a matrix is called B, then its determinant is denoted like that. And also, if a matrix is called C, then its determinant is denoted with the letter C and 2 strokes. So why am I pointing this out? Because sometimes CXA gives you this symbol and you must know it means determinant. So this would be the matrix itself. This would be the determinant of matrix A. This would represent matrix B itself, but this would represent the determinant of matrix B. This would represent matrix C itself, but this would represent the determinant of matrix C. So if you see this, it means the determinant of matrix C and not matrix C itself. If you see this, it means the determinant of matrix B and not matrix B itself. So this means the matrix, and this means the determinant of the matrix. So we're going to get in that so you see clearly what I'm talking about. So we're going to look at now finding the determinant of a 2 by 2 matrix. All right, so focus on example 1 for me. So we're looking at this. Now, there's something that you need to know, which is important. Now, obviously, this is a 2 by 2 matrix, and the elements are 3, 1, 4, and 5. Now, before we proceed, there's something that you need to know, which is referred to as the diagonal, or the leading diagonal of a matrix. The leading diagonal of a matrix. Now, the leading diagonal of a matrix would be these elements here. Those elements would be in the leading diagonal. So, what we mean by leading diagonal. Okay, so these elements would not be in the leading diagonal. They would be in the non-leading diagonal. So these elements are in the leading diagonal. Similarly here, let's just do this same time. These elements here would be in the leading diagonal. Leading diagonal. Anyway, let's go back to example 1. So we're given matrix A here, which has the elements 3, 1, 4, and 5. And obviously, it's a 2 by 2 matrix, as you can see, and we're asked to find its determinant. So the determinant, which is denoted like this. Now, CXC didn't have to write the word determinant here. Once they put that symbol, you should know that it means the determinant of matrix A. So let's go ahead and find the determinant. Now, it's very, very simple, very, very straightforward. So the determinant of matrix A would simply be equal to the product of the elements in the leading diagonal, the product of the elements in the leading diagonal, which would mean 3 times 5, minus the product of the other elements in the non-leading diagonal. So it would be 1 times 4. So again, the determinant of matrix A would be equal to the product of the elements in the leading diagonal, and we already identified the leading diagonal here, minus the product of the other 2 elements, which would be 1 and 4. So what we have here is 15 minus 4, 11. So that means that the determinant of matrix A is equal to 11. As simple as that. But you can't make any mistakes now, and you have to be double careful when you see negative signs floating around like in example 2. So let's look at this one. So given matrix B is such, again, only dealing with 2 by 2 matrices, and we're asked to find the determinant, which is denoted this. So we're going to just do that now. So the determinant of matrix B is equal to the product of the elements in the leading diagonal, and you can clearly see that the elements in the leading diagonal are -1 and -2. So the product of those 2 elements minus the product of the other 2 elements, which is -3 and -6. So we're just going to put that there. All right, so this would be equal to -1 times -2 is 2, minus, be careful of this minus and other negatives in the bracket, So it's minus, and of course negative 3 times negative 6, that would be positive 18. So 2 minus 18 is negative 60. So the determinant of matrix B is equal to negative 16. So we can always just denote just like that. The determinant is equal to negative 16. So these are two examples here in showing you how to find the determinant of a 2 by 2 matrix. Let's look at these two. Again, notice I've opted to take out the word determinant because you should now know that this symbol here means determinant. Here's what I don't want to happen. I don't want anybody, for example, I'm just showing you this one. This is matrix C, which is that. If you were to do something like this, just pointing this out right away. If you were to do something like this, I'm just going to pull this back a little bit. If you were to make a mistake and do something like this, right? This wouldn't make any sense whatsoever because this symbol here means determinant, and the determinant is a single value. So this doesn't make any sense. So right away off the bat, crushing that up. All right, bye. All right, so let's take a look at this. Again, we're focusing on 2 by 2 matrices only. So we're asked to find the determinant of matrix C, which is denoted this way. So the determinant of matrix C equals the product of the elements in the leading diagonal. Here are the elements in the leading diagonal. That would be 10 times minus 1 minus the product of the other two elements, which would be negative 5 times 1. So 10 times minus 1 is minus 10 minus, in bracket, be careful, this minus is different from the other minuses here. So minus 5 times 1 is minus 5. So negative 10, negative sign changes signs in brackets, so that would be positive 5, and we would have negative 5 for the determinant of matrix C. Coming over here, it says, given matrix D is that, find the determinant, or find its determinant. So the determinant of matrix D would be the product of the elements in the leading diagonal, so that would be 8 times 2 minus the product of the other elements. So it's 4 times 4. That would give you 16 minus 16, which is 0. So there you go. So you should have a very good idea now how to find the determinant of a 2 by 2 matrix. So be careful in how you rush it, and especially when it comes out to negative signs, like in particular this case. So watch out for those things there. All right. Now, important here. Now, I'm going to give you the notes first and then summarize it so it's easier to remember. So, if the determinant of a 2 by 2 matrix, as of course is 2 by 2 matrices we're dealing with, so it says if the determinant of a matrix is equal to 0, if the determinant of a matrix is equal to 0, the matrix is said to be singular. So, if the determinant of a matrix is equal to 0, remember when you're looking at types of matrices and we mentioned singular and non-singular and said that we would come back to those later down in the topic. Well, this is later down in the topic. So, if the determinant of a matrix is equal to 0, the matrix is said to be singular and will therefore not have an inverse. So, if you calculate the determinant of a matrix and you find that that value is, or the determinant is 0, then that particular matrix is singular. And the thing that we know about singular matrices is that they don't have an inverse. You'll understand that a little later, but just take it for now. So if the determinant is 0, the matrix is singular and will not have an inverse. Now, however, if the determinant is a non-zero, so remember when it's 0, it's singular and does not have an inverse. However, if the determinant is a non-zero value, meaning any number other than 0, so it could be negative or positive, it could be 3, it could be negative 4, as long as it is not 0. However, if the determinant is a non-zero value, the matrix is said to be non-singular. Non-singular and will have an inverse. Okay? So again, if you calculate the determinant and you get 0, then the matrix is singular and it doesn't have an inverse. If you calculate and get a non-zero value, whether positive or negative, then the matrix is said to be singular and it will have an inverse. So, in other words, singular matrices don't have inverse and non-singular matrices have inverse. Now, let's just summarize it quickly. Oh, before we move on to that. Let's summarize. So, let's summarize. So, let's take a look at this. If determinant equals 0, matrix is singular and does not have an inverse. So, once determinant is 0, matrix is singular, no inverse. If the determinant is not equal to 0, any other value. Once it's any other value other than 0, then the matrix is non-singular and it will have an inverse. So in other words, for a matrix to have an inverse, it must be non-singular and it must have a determinant that is not 0. In order for a matrix to not have an inverse, it must be singular and the determinant must equal to 0. Now, having said that, let's take a look at what the examples that we looked at. Based on the fact that in example 1, our determinant of matrix A, so matrix A is this. The determinant that we found is 11. Now, based on what we read, would matrix A be singular or non-singular? Well, since the determinant is 11 and 11 is a non-zero value, then this would be non-singular because the determinant is a non-zero value. It's 11. Once it's any other number apart from 0, it must be non-singular. Let's take a look at this matrix, which is matrix B. We found that the determinant is negative 16. So once it's a value other than 0, then matrix B is non-singular. Okay? So these two matrices would be non-singular because their determinants is a non-zero value. So let's get that out of the way. Let's take a look at this. Now, matrix C is that. Our determinant for matrix C is negative 5. So would matrix C be singular or non-singular? This matrix here would be non-singular. It would be non-singular. Now, matrix D is this matrix. When we calculate the determinant, we found that the determinant is equal to 0. What does that mean now? It simply means that matrix D is singular. So this one for sure is singular. Why? Because its determinant was found to be 0. So this guy here is singular. And when we get later down on the topic, you can understand why this guy would not have an inverse. Right? You're going to find out why singular matrices do not have an inverse. All right? So we're going to get that out of the way. Now, here's an interesting question. Now, it says, given matrix A, of course, it's a 2 by 2 matrix, and it has elements x, 2, 9, and 1. And you're also told that matrix A is singular. What does that mean? It means that when you calculate the determinant, you're supposed to get 0, right? It says, now determine the value of x. So we're going to go ahead and do this. So this is how you'd approach a solution to a question like this now. You're given a matrix, there's an unknown element there. This would be the leading diagonal. You're told that matrix A is singular, which means that the determinant must be equal to 0, and we're asked to find the value of x. So here's how we approach it. So the determinant of matrix A would be the product of the elements in the leading diagonal minus the product of the other two elements. Now, because matrix A is singular, we know that when you work out the determinant, you're supposed to get 0 because you're told that it is singular. Now, x times 1 is x. 2 times 9 is 18. All we have to do is make x the subject. How do we do that? So we carry over the negative 18, so it will be 0 plus 18. which is equal to x, and 18 would be equal to x. And it makes sense there. So why does it make sense? Because if we replace x here and put 18, 18 times 1 is 18, minus 9 times which is 18 would give you 0. So it makes sense. So this is how you'd approach doing a question like this, that is focusing on singular matrices. And of course, if a matrix is singular, the determinant must be equal to 0. Next question. And we're going to actually close off the video with this one. So, same thing. Determine the value of y in the matrix below if the matrix is singular. Again, if the matrix is singular, its determinant must be equal to 0. So, here's how we approach this one. So, the determinant of matrix B, elements in the leading diagonal, so it will be the product of those two elements, minus the product of the other two elements. Alright? So, since seeing that the matrix is singular, the determinant must be equal to 0. Minus 3 times 4 is negative 12, and 6 times y is 6y. Now, in this particular case here, you can opt to carry over the minus 12 or opt to carry over the negative 6y. Now, they want me to find the value of y. So I'm going to move minus 6y because it's negative. When I carry it over, it must become positive. So carry this over, it would become 6y. There's 0 here, so it doesn't make a difference whether I put 6y plus 0. It's just 6y minus 12. And of course, y would be equal to negative 12 divided by 6. So the value of y would be negative 2. So that is how you go about working out problems like these that involve singular matrices. So here it is that we just looked at how to find the determinant of a matrix and 2 by 2 matrix and the significance of the value in terms of the answer when we do calculate the determinant of a matrix. So again, what I want you guys to do is review this video as many times as you wish after the session, and then just give me some general feedback. All right. So I hope you found this video insightful, and I'll see you guys on the next video.